Hello, everyone. Welcome back. Today, we want to talk about limits and specific limits. I'm calling this limits and infinity. Meaning we're talking about two kinds of limits. Limits where the result is infinity or negative infinity, or the other limit in cases where actually take the limit as we go to infinity or negative infinity. For goals, as you can see over here on the left, so we define limits of functions whose limits are equal to infinity or negative infinity. You see where that happens. Also be the final limits at infinity. When you go toward infinity or negative infinity for a function, you'll identify asymptotes of a function. We'll see these kind of asymptotes over types can result from, if you look at the behavior of certain functions, especially far close, possibly close to zero and far from zero. And also determine the behavior of function far from zero based on the exponents of the terms in the numerator and denominator of the function. We'll explain what that means. So let's talk about limits equaling infinity. So what happens if you have a limit that actually the result is infinity? So if a function increases or decreases without bound as a limit approaches a specific number, then the limit is equal to infinity. Actually, there should be a let me go ahead and correct that. There should be, I should say, and if the function increases, decreases, oh, there are some copying and pasting errors here, decreases. The function decreases without bound, then the limit is equal to negative infinity. Okay. Actually, hang on just a second. Oh, no, actually, it's sorry, just a second. Actually, I was right to begin with. So sorry about that, the confusion. So approach a specific number, then the limit is equal to infinity if the function increases that bound. And the limit is equal to negative infinity if it decreases that bound. So let's take a quick look at an example over here. And a familiar example. So let's look at some examples specifically of 1 over x. Okay. Now then let's go to Desmos. So for Desmos, go to DES MOS. There we go. I think my internet may be a little bit slow. All right. So if we just type in just 1 over x, you type in y or not. Okay. So this is what function looks like. And you may have seen me show you this in a previous video introducing limits. Now, specifically, let's take a look at what happens when we get close to zero. So you notice this has this kind of this weird sort of gap right here. That's intentional. Because you remember, if x is zero, then this is undefined. Okay, so x can't be zero. So what happens then, let's think about what happens as x approaches zero. So it doesn't matter where we start. Let's approach zero from the right. So as x is closer and closer to zero, the x coordinate gets closer to zero. What happens, the y coordinate starts increasing. Okay. And basically, if we zoom out a bit, we'll zoom out quite a bit. What happens is the further we go, the larger it gets. So here we're getting closer and closer to 0.05, and this is at 20. Okay. Now, if you keep on going, it's going to get larger and larger. All right. And eventually actually goes to infinity. Okay. Now, similar kind of thing happens the other side. So as we get closer and closer to zero, the x coordinate gets closer to zero from the left for negative values, gets closer and closer to negative infinity. For some reason, that's not dragging correctly, but you see what happens. Okay. And that's because, the thing about this, our numerator is always 1. So the smaller I make x, the larger this gets. Okay. So I can, regardless whether x is negative or positive, it gets larger in a positive or negative direction. All right. So let's go back to our back here. So what we can say then is, of course, here, comma, of course, x can't be equal to 0. It's undefined there. So the thing about the limit as x goes to 0 from the right, that's what we said. Actually, we say goes or equals positive infinity. Okay, base increases that bound. The closer you get to 0, the closer it gets to infinity. Of course, it never actually reaches it. Remember, infinity is not a number. That's what happens. And we think about the limit then as x goes to 0 from the left. We said that equals goes to negative infinity. It decreases with that bound. Okay. There's some examples of that. All right. So that's what can happen. So what can happen, we approach a negative, approaching any specific number, and our function either increases or decreases that bound, then that's what's called limit basically equaling infinity or negative infinity. Okay. Let's go back to the left. Our next topic, then, which we're going to use some today, is rational functions. This hopefully some of you remember somewhat from algebra. So rational functions called f of x looks like this, where we have on top we have g of x, at the bottom we have h of x. Our functions g and h are polynomials. Remember, polynomials are nice functions, and we can say this as long as h of x is not 0 itself. It can be 0 parts, but it can't be 0 itself. Okay, and it says where the numbers where h of x is 0, there's either a hole in the graph or a vertical asymptote. And also I mentioned there's a hole in the graph, and there's probably usually some common factor between the numerator and denominator. Okay. So let's take a look at a couple examples of that. And actually, let's go to, let me mention one more thing. I want to mention a vertical asymptote, because that will come into play here in just a moment. So a vertical asymptote is a vertical line, x equals a. Remember, a vertical line has an equation, x equals a number, where a is a number. So if you plug in a to the function, it's undefined. Okay. Graph of function approaches never touches a vertical asymptote, and also the graph never crosses a vertical asymptote ever. Okay. And at a vertical asymptote, your limits from left to right either go to infinity or negative infinity. Okay. So for example, back here to our example of 1 over x. So if I think about the graph of 1 over x, sorry, I don't know what caused that. So the graph looks like this, and I'll show this on Desmos again. Okay. So we have a vertical asymptote. Kind of hard word to spell at first. At x equals 0. Okay. And we can see that if we go back to Desmos. Let's zoom in a bit more, make this more clear. All right. If I also graph the line, I can also graph vertical lines of Desmos, x equals 0. We can see that, and we can actually see then that the function approaches that vertical asymptote. Okay. Let's get another example. Let's make this, or let's call this, once again, we call it f of x. Let's make f of x is 1 over, say it's x minus 3, and then x plus 2. Okay. Now, similarly, as we can see, what numbers make our function, this function 0, or denominator 0, is one is positive 3, so x can't be positive 3. Make this part 0, and also x can't be negative 2, so make this part 0. All right, so let's graph that. So, as we'll see, you might expect we actually have vertical asymptotes at those points. All right, let me actually just, I'll just turn these off right now. I might come back to them later. Let's do this. So 1 and then divided by parentheses x plus 3 and x minus 2. Okay, that's kind of a somewhat interesting graph. So as we see what happens, right, we have these gaps here, and we just said x can't be 3 or negative 2. So actually, if we draw two vertical lines, x equals negative 3, where the function is undefined, and at x equals 2, we can see we have two vertical asymptotes there. But think what happens to our limits, we have similar sorts of things here at our limits. Okay, so think about the limit as x approaches negative 3 from the left, goes to positive infinity. If it approaches negative 3 from the right, it goes to negative infinity. Okay. Now, also one thing, these sometimes they may both approach the same. Sometimes functions could approach the asymptote from the same direction. That happens sometimes. Okay. Um, but in this case, they don't. So let's go back, and as we saw here, so we think about -3. We approach -3 from the left, it goes to positive infinity. Approach -3 from the right, it goes to negative infinity. Is equal to positive infinity, then the limit as x goes to -3 from the right, f of x is equal to negative infinity. Okay, right. And so in this case, those are both asymptotes because um, both made the function 0 at those places. The function was 0, the denominator was 0 at both those places. And because it was 0, then we had a vertical asymptote. You notice that, of course, the denominator was 0, so 0. Okay. Let me check something real quick. So let me change that just a moment, see what happens. Okay. Now there's a good example whereby changing that, I actually changed my asymptotes. But actually, by changing this, I should have pressed up here. In this case, that has opposite behavior too, right? So here's what happened in that case. All right. Now, so that's a vertical asymptote. And as we'll see, you don't always have vertical asymptotes. Okay. So let's look at an example, our next example. We have a case where we don't have ooh, what just happened? That was something else. Okay, let's look at our next example, number 3. Okay, so this time let's look at this function. I'm actually call it g of x this time, just to call it something different. G of x equals x squared minus 3x minus 10. And my denominator for my numerator is going to be x squared plus x minus 2. Now, a good thing to do when you have something like this, right now we're not yet exactly sure where our denominator is going to be 0. So let's scrap it, get an idea of what it looks like. That can often lead us in the right direction. So actually, I'm going to go back and just kind of, this gets a little complicated, just close all these. So let's do that. Now, let's get, we'll put something in the numerator like this, need parentheses. So x squared minus 3x minus 10. And then that's divided by x squared plus x minus 2. Okay. If you notice, you have some kind of a gap here, but actually there's only one. So it looks like there's definitely an asymptote here somewhere. Can't exactly see where it is. Okay. But also it appears there's only going to be one asymptote. Okay. Like the last one where we had 2. Let's get an idea of what that might be. Okay. Now, once again, wherever the function is equal to 0, wherever the denominator is equal to 0, we know the function basically can't exist there. So actually, we factor this. And we're not going to discuss how to factor, hopefully some of you remember, but so if we factor this, this factors into, numerator does x plus 2 and x minus 5. And then down here factors into x minus 1 and x plus 2. Okay. Now, what we notice then right away is from this is that x can't be positive 1 and x can't be negative 2. Now, that's, ooh, that's bizarre. That's true regardless of whatever the numerator is. Okay, then it doesn't necessarily mean, as we saw, it doesn't necessarily mean we have an asymptote in either place, because these will actually cancel out. As long as we're not equal to, as long as x is not equal to -2, these will cancel out, be left with x minus 5 over x minus 1. Okay, so what that tells us then is we have a vertical asymptote at x equals +1. Okay, because that's still left over, doesn't cancel out. And so that's still undefined there. And then we have a hole in the graph at x equals -2. Okay, so let's take now, let's take a look back at our graph on Desmos, see if that makes sense. Okay, so let's draw the vertical line, x equals 1. And see, zoom zoning approaches further we get from x, and then at -2. Yeah, so I think, yeah, if you just get hit, it's hard to hit that, but it's -2 right there is undefined, because it's undefined, once again, as we said, because even though there's no asymptote there, the denominator in the original function is equal to 0 there. And so it actually, this is it. So it can't actually be, the function just doesn't exist. Let's go on down. Let's actually graph that on our paper here. Vertical line. Okay. So this is x equal 1. And so this graph looked like, back here, make sure. Okay. So it looks like this. This. Okay. And then we said there's a hole in the graph right here at x equals -2. Okay. Now, once again, think about the limits, then, as you limits as x goes to 1 from the left, goes to positive infinity, as x goes to 1 from the right, goes on the right, goes to -infinity. Okay. Now, there's also some behavior out here we're going to talk about here in just a minute. Okay. Notice, looks like, let's go back to our graph. It looks like, if we zoom out again, looks like kind of left, and we're just living off of specific numbers. So we've traced this out. It looks like it's maybe getting closer and closer to 1 in this direction as we go in a further larger and larger negative direction. Larger and larger positive direction looks like maybe it's getting kind of close to 1 out here. As we'll see, it is. We'll talk about that in a moment. Okay. So that's the idea of vertical asymptotes. Now let's talk about limits at infinity. That's our next topic. We'll actually come back to these same examples we just. Let's come back to the left. Limits at infinity. This happens when we think about take x toward either infinity or negative infinity, get larger and larger in a positive or negative direction. What happens to our function? Okay. So as we take a limit as a function x goes toward infinity or negative infinity, write it like this. So what we're going toward is infinity or negative infinity. And these limits could be equal to constant, or they could go to positive infinity or negative infinity. Depends on the function. This one we'll explain here in a moment. Okay. Also, one thing to mention, if we talk about the limit going toward infinity, that's the same as going to infinity from the left, because it can't go to infinity from the right, because that doesn't exist. That doesn't make sense. We can't be bigger than infinity. Same way. So I can't, if I approach infinity, like on this graph, I have to approach it positive infinity, I have to approach it from the left. I can't approach it from the right. That doesn't make any sense. In the same way, if I go to negative infinity, I must approach negative infinity from the right. It doesn't make any sense to talk about approaching it from the left. Because that would be saying you're further away from 0 than negative infinity to do that. That doesn't make any sense. Understand? Now, happen of asymptotes. We can get two other kinds of asymptotes. One is what's called a horizontal asymptote. So that's a straight line, a horizontal line, the base of the function approaches. Now, one thing's different about a horizontal asymptote than the vertical asymptote is the graph can never, ever cross a vertical asymptote. That's where the function is undefined. But a function can cross a horizontal asymptote close to zero, but it won't cross it far from zero. You also get something called a slant asymptote or an oblique asymptote, where instead of approaching a constant line, okay, y equals m. Okay, so similar in a sense to the horizontal asymptote, where if your function is approaching zero from, or basically if you're close to zero, a graph can cross an oblique or slant asymptote far away than it doesn't. So let's actually take a look back at the functions we just talked about, because these actually do approach horizontal asymptotes, okay? So we didn't mention it here, but actually both of these, I'll go ahead and pencil in right here. Sure, I have my drawing tool. So the graph y equals zero is a horizontal asymptote. Okay, because if you think about this function once again, our numerator is constant. So as x gets bigger, either direction, this whole thing gets smaller, either positive or negative. The whole thing gets smaller and gets closer and closer to zero, the larger I make x, either positive or negative direction. Okay. Then the function down here, also, this is true of it as well. Okay. This function, actually, I forgot to write this in. Of course, we have vertical asymptotes. At x equals 3, x equals -2. And in the same way, here, my numerator is constant. So the larger x is, either positive or negative direction, the bigger my numerator will get. It's going to be positively or negative. The absolute value will get larger. The whole thing will get smaller. So we have a horizontal asymptote. At x equals 0. Okay. Now, let's go back and take a look at this one. Now here, interestingly, what happens is actually, as we saw, let's look back at our graph. Let's go zoom out again. Let's zoom out quite a bit. Okay. Let's see, if you trace it along, as we see, as our x coordinate gets larger and larger, our y coordinate keeps increasing, but that's what's going to happen is it's closer and closer to 1. Okay. And the same way over here, in this function, as my x coordinate gets larger and larger in a negative direction, goes toward negative infinity, this also decreases toward 1. So in both cases, my horizontal asymptote is actually 1 for this function. And I can also draw that as a dotted line. Try and draw a straight line here. So that's going to be at y equals 1. That's a horizontal asymptote. Let's abbreviate horizontal asymptote. Let's abbreviate that. So what that means is, look, what this says is the limit as x goes to infinity, as we go in this direction, of f of x is equal to 1. Then over here, if I do the limit as x goes to negative infinity of f of x is also equal to 1 in this case. Okay, they're also equal to the same. Okay, and we'll hear in a moment we learn why that's the case. Now, let's talk about next, go back to the about the behavior, right? Why this happens. Okay. So let's look over here. And this is kind of more mathematical looking things we're going to see today. So a rational function, remember I said it had a polynomial on top, a polynomial on the bottom. Okay. Now, the behavior of the rational function far from zero, okay, as we go toward infinity or negative infinity, is determined by what are being. So if you recall, the highest power for, and this